Hey guys, today we're gonna start working on the second chapter in historical geology. It's titled Rock, Fossils, and Time. So make sure that when you read it in the book, you look for this title name, whatever chapter is it, whatever type of book you use. This is the chapter you're looking for. Um, so let's jump. The sedimentary rocks, you got to understand, are really, really important in historical geology because they have a lot of information about the way they formed. It's about the environment, how much oxygen has been in the environment. Uh, and we can really use the sedimentary rocks as a puzzle to put together, puzzle pieces to put together the whole historical geology and earth history. So therefore, we're going to really emphasize the sedimentary rocks. That doesn't mean that you don't have to remember igneous or metamorphic rocks, because actually they can carry information about a lot of things like environment. However, the sedimentary rocks are much better in most of the cases than environmental information gathered out of igneous or metamorphic rocks. So let's jump in and see what kind of properties we're going to have to really look at in the sedimentary rocks. And you can see here like the color, the texture, grain size and sorting, the shape of the grains, sedimentary structures, and then after we looked at all this, we're going to talk about the maturity of the sedimentary rocks. So these are very important information. Each of these things will be able to tell us stuff about how these rocks form, what kind of environment, what kind of climate, and stuff like that. So let's start with the color. Remember, I have told you a couple of times that probably the color of the rocks is not necessarily very meaningful. Like I told you that sedimentary rocks like limestone can have any kind of colors. However, there are cases, situations, especially in case of the sedimentary rocks, when the color does give you a whole lot of information about the depositional environment. And remember, we actually went through the different possibilities. So I'm going to start with the black or dark color. When you have black or dark colored sedimentary rock, that will mean that it has undecayed organics present. And if you look around on the surface of the earth, when a tree dies, what's going to happen to it? Is it going to decay or is it going to stay undecayed? Yes, you're right. It's going to decay because there is oxygen, and oxygen will actually slowly burn. You're not going to see flames or anything, but still reacting with the organic material, it actually slowly decays it. So therefore, when the color is black, that means that it does contain some undecayed organic material. So the fact that they are still present means that around these environments there was no oxygen. If there is no oxygen present in these environments, the iron will have two charges, two positive charges, and it will form minerals in that way, like pyrite, that's FeS2, and it will form hydrogen sulfide, would accumulate, which doesn't have iron, but the main thing is that the iron, the two positive charge iron will react with sulfur instead of oxygen. You know, when you have a lot of oxygen around, the iron will react with oxygen and will make iron oxide, which usually is red or brown. So in these cases, not only pyrite will form almost all the time, but I already mentioned the hydrogen sulfur, that ratneck smell. The hydrogen sulfur will be very, very common in black shales. So if you have a house where the water well has this ratneck smell, like I go to Georgia a lot to my brother, and his water is like that. That just means that it's coming from layers. The water might have coming from layers where there is dark shale with undecayed organics, and that's where the rotten smell is coming from. And if you see black shale with pyrite in it, that's very normal. because this is the environment for pyrite formation. That's why we do have the problem with the coal, because every single coal basically is undecayed organics. So therefore, every coal is full with pyrite. And when you put it in the coal burning power plant, actually it will produce sulfuric acid. That's what makes the acid rain. So it's a problem. And coal forms in this kind of environment where there is no oxygen present. We'll talk more about it. On the other hand, if the color is red or light, that means light brown, reddish brown, white, yellowish, so these ones right here. That means that there was plenty of oxygen around when the rock formed, and the iron had 3 charges, 3 pluses, so in this case it will react with oxygen and makes hematite, magnetite, or like the oxidized type of iron. And in this case, there is absolutely no undecayed organic present. So this is what you kind of have to know about the color. So it will tell you if the environment was oxygen rich or if the environment was oxygen poor. And now I have this slide here, and that just shows you how the color relates to the environment. So as you can see, the black and dark color, which includes the undecayed organics, will always, just about always, form in deep or stagnant water. Where would you have stagnant water? Yeah, you would have them in the marshes, in the swamps. If you go to Virginia Beach, there is Virginia Beach State Park, and right there you can walk on the boardwalk, and you have this huge big water-loving pine trees, and the water around it, it's like swamp, and it's really black, and the sediment is very fine-grained. So if a tree dies, falls down, then it gets covered with clay, so it will never actually be able to oxidize or decay. So those are the environment where you have undecayed organics, so the rocks are going to be dark or black colored. And you can see as the color is getting lighter and lighter, you more or less going toward the continent. When I say terrestrial, that means continent. Continent. The next physical property is the texture. And when you're talking about texture, you're really talking about the size, shape, arrangement of the mineral and the rock fragments in the sedimentary structure. And the parts you're looking for are the grains. Those are the larger particles. The matrix, which is the finer particles. And sometimes there is cement between the grains, and those are chemical precipitates. You know, that's what glues the particles together. And right here I have a picture where you can see the clasts or grains, the matrix, which are the finer particles, and then there is the cement, which glues the particles together. And this one is about the grain size. And the grain size we learned last semester, and I think that's going to be enough for this semester too. Probably we have the possibility in the lab to really use the Wentworth scale. That's what they use in technical labs when they want to analyze the soil sample by the grain size. They have this different size separation apparatus, and they can separate the grains by grain size. As I said, you will do it possibly too. But I want you to know the gravel size, which is larger than 2 millimeter. Those are the pebble size or gravel size, or however you want to call it, larger than 2 millimeter. And then the sand is, you know, we learned it at the time last semester. The sand is from 2, sorry, the sand is from, sand comes here, from 2 millimeter to millimeter 0.063. And if you divide 1 over 16, that's what you're going to get. So 0.063, remember I have told you that 0.063 is actually the lines on your fingertip, the thickness. So when you touch the sandstone, you can feel the grains. And the 0.063 is going to be the siltstone, and that is when the grains are smaller than the thickness of the lines on your fingernail. So when you touch the silt, which is one below, you can actually, you won't feel the grains. They are going to go into the line, so your hands are going to get dirty. Where if you touch sandstone, it won't, because the grains are bigger, so you feel the grains actually when you touch it. The silt is going to be between 0.063 millimeter to 0.005. So 0.063, 0.063 to 0.005. So 2 zeros and a 5. 2 zeros and a 5. And that's the siltstone. And the clay is less than 0.005. So that is bigger than the clay. So remember, you don't need to know this, what says here. However, if you make the division, it's going to be exact. So the pebble is larger than 2 millimeter. The sand is between 2 millimeter and 0.063 millimeter. The silt is between 0.063 to 0.005 millimeter. And the clay is less than 0.005 millimeter. So that's the size distribution of the sediment. And here this picture shows you the sorting. The sorting is basically the grain size distribution. If a sample is all sand size, like 2 millimeter, then every single one of them is like that. So it's very well sorted. And if you have sediment which has every kind of grain size in it, that's very poorly sorted. And then you have the ones in between, which you can say pretty well sorted or relatively poorly sorted, or you can name it however you want it. And this one shows you example for each. This is a very well sorted coarse sand. And if you look at the distribution curve, like the grain size distribution, this is the grain size and this is percentage. If your sediment is well sorted, then the grain size are all belonging to the same grain size. The grains belong all to the same grain size. So therefore, you're gonna get a distribution curve like that. Basically, every grain is exactly the same size. On the other hand, if you have a very poorly sorted sediment, then it's gonna be like this. That just means that each grain size is represented, and it's not that much. Either one of them is not that much. So that is a big difference between poorly sorted and very well sorted sediment. Remember, poorly sorted would happen like if you had a glacier or if you had a mass movement, like a mudslide or rock slide, or every kind of grain size goes down. And the well sorted would be like if it was wind carried. Most likely if it was wind carried, like you would have it in the sand dunes, or yeah, the wind carried will do the best sorting. And remember, we talked about the river. The river has at least 2 major grain size, because you have the grains which are being carried on the bottom, the bigger grain size, and then you have the suspended load, which is like siltside sediment in the river. So the river will have at least 2 major grain size in it. So here on this picture, I just want you to tell me, what do you think? Is it well sorted or poorly sorted? What do you think about this one right here? Yes, you're right, it's well sorted. How about this one? It's poorly. It is a very typical glacial tillite, so it's very poorly. See, you have every kind of grain size. How about this one? Poorly, you're right, you're right. It has every kind of grain. How about this one? Now be careful, the color difference shouldn't mess you up, because here the grain size is exactly the same for every single grain. There is just color, means that it has different minerals in them, but the grain size is the same. And this slide is about the shape of the grain. The shape of the grain is going to talk to you about the distance the grains have been traveled, because as they go through the sedimentary environments, actually on the way they get kicked, depending on what kind of transportation material transports them. Like if it's the wind, think about, if it's the wind, there is nothing in between the grains, so they kick each other all the time. That means that they're gonna get rounded really quickly. If it's in the river, then each grain is gonna be surrounded by the water, so eventually it will get really rounded, but not that fast as in the wind. And if you're in the glacier, every single grain is surrounded by snow, so the grains don't kick at all. So they are not going to get rounded whatsoever. So this really helps us. If you look at the grain's roundness, it really helps us to pinpoint how much distance have they traveled and what kind of material transported them. So these are very important characteristics here. And these are the different shapes you can characterize your particles by. And there is two major issues. Like if you have like a rock, such as granite, or you have marble, they tend to become completely spheroidal. Like they're gonna be spheres when they become rounded. So this is how it looks when it's angular, and this is how it looks when it's rounded. On the other hand, if you have a metamorphic rock, like you have a microschist, if you remember that, it will never be able to make this kind of pebble, because it just has such a linear appearance that actually, even if it becomes the most rounded, it's still gonna be oval shape. So you have to see if the original rock has high sphericity, we call it, or if the original rock has low sphericity. So you have to take that into consideration. It's important. So this here is just a little card which I will have for you in the lab too when you have to define your rocks. And this just like shows you all the things: the grain size, the shape of the grain, the sorting. So it helps you to tell what kind of rock do you have here. Now we're talking about the sedimentary structures. Remember, the sedimentary structures also just a reminder from last semester, because we have gone through them. So I'm just bringing up one picture of each and mention it. So if you don't remember or you haven't had physical, just try to catch it. You can ask me later or in lab or something. Anyhow, I have to stop here because my clock is at 18 minutes. I'll continue in the second segment.